does not figure, so we have 1 and 2 and 3 and 4 and 5 and 6 and 7. And so this is your Q0, this is your Q1, this is your Q2, and this is your Q3. And that definition, the way in which this is constructed, is of course very clearly satisfied. Each node in Qi plus 1 is a neighbor of a node in Qi and has not been visited yet. And so again, you're going to get your array visited in the same way as we did it before. And so in that particular case, it follows that you have, again, a consistent answer. 1, 2, 3, 4, 5, 6, 7 can be visited from 1, but 8 cannot be. And so if we were to start with 8 depth first, well, you would have 8, and then you would have 7, and then you would have 3. So in this case, this is kind of boring. And then you would have 5 and 4 and 6. So this is Q0, Q1, Q2, Q3, Q4, and Q5. And so that would then give you the Qs if 8 were the starting point. Now we have to look at the question 1. Can we reach V from U? And that is relatively straightforward. It basically is answered by either one of those two algorithms, depth first or breadth first, because ultimately the only thing that is relevant in this case is U. And the V sort of is an afterthought, if you will, in the sense that if you go and start with U and you run through the process, both in depth first or in breadth first, then at the end you can decide what V you want to see. And obviously each V that is recorded as true in the array visited is going to be reachable from U, and any V that is not recorded as having been visited, not recorded with true, is obviously not reachable. So in some sense, we are looking at a question of termination. When do we terminate in depth first, and when do we terminate in breadth first? Obviously, you can say I'm going to terminate as soon as I encounter V in each of those two processes, and that is certainly a correct answer, because it will tell you, yes, V can be reached. However, what if V is not reachable? How do we terminate? Or if we just want to go on and leave the V unspecified until after we finished everything. So how do we terminate? Well, in the case of depth first, you basically keep doing your recursive processes until you've exhausted all possible ways of going through. And so, as I said, in the case of U being 1, you start with 1, and then you go down to 2 and 4 and 6 and 5, and then you backtrack 5, there is nothing. Then 6, there is nothing but for the 5. And then 4, we've done the 6, but now we have the possibility of doing the 7. So we do the 7, and then we go down to 3. And 3, there's nothing. And so we backtrack to 7. There's nothing else other than the 3. Then we backtrack to 4. There is nothing else except for the 6 and 7, which we've done already. So we backtrack again. Then we have 2. There is nothing that we can do. There, backtrack 1. Well, there is 3, but 3 has already been visited. So we backtrack again to 1 and stay there, and because this is the starting point and there's nothing else, this is then actually the termination condition for depth first. We've completed the entire recursive process. In the case of the breadth first search, the termination condition is perhaps somewhat simpler. Basically, it is the requirement that we end up with an empty queue. So if you look at Q3 in this case, well, there is 6 and 7, and from neither 6 nor 7 do we get anything that we haven't visited. From 6 we go to 5, which has already been here, and from 7 we go to 3, which has already been visited here. So neither 6 nor 7 are going to give us anything that satisfies this requirement, and that means that the next queue, Q4, would be empty. And that is the termination condition. We go on with this process until we encounter an empty queue. And that means that that is the end of it. So at that point, we now know that 8, for instance, can't be reached because can't be done. It is not the neighbor of any of the nodes that we have encountered, and therefore it does not figure in that. So we have these termination conditions, and that means we now know how far we have to go and when we have to terminate. So that then allows us to start looking at these questions. We've already said that the first question can be answered by either one of those two. We can do it with a breadth first, or we can do it with depth first. Either of these two methods will be perfectly acceptable and will give the correct answer, yes or no, for any particular V. Now, the second question is more interesting because, as you can see, if you look at those queues, they don't really give you a path. They give you queues, and we know that Qi plus 1 contains all nodes that are neighbors of some node in Qi and have not been visited before. So that is certainly true, but it doesn't really give you a path. So if you want to go to 7, you can't say, well, there's a path from 1 to 3, 3 to 5, 5 to 7. If we look at that, 1 to 3, 3 to 5, 5 to 7, 1 to 3, 3 to 5, that's fine, but 5 to 7, there is not an edge. There is a path, but that would suggest that distance is much larger. It's one more than what it really is. So the path is 1, 2, 4, 7. But how do we know that? On the basis of these queues, we don't. So the upshot of that is that breadth first, in and by itself, does not give us any path. It will only give us, as we will see, the distance. But it doesn't give us the path. In order to get a path, we have to go with depth first. Depth first, as I've already said, is a recursive method in which a path to a node, which is the top of the queue at this point, that path is going to be in the, top of the stack. A path to the top of the stack is precisely in the recursion stack in the reverse order. So if I want to go to 7, then I have 1, 2, 4, 7. That is my path. And the recursion stack will contain 7, 4, 2, 1, which is the reverse order of this path. And similarly, if I want to go from 1 to 5, well, I go down there. I have 5 on top of my stack, and 5, 6, 4, 2, 1 would be the content of the stack in that order, and the reverse of that is, of course, 1, 2, 4, 6, 5, which is a path. And so depth first very clearly gives me a path. Breadth first does not. So that means that that second question, find a path from U to V, can be answered, but it requires an application of depth first only. It will not be answered by breadth first. Now, there's a third question. What is the distance? Well, that is, of course, a question that we've already hinted at, alluded at, when we dealt with breadth first, because obviously the number, the index of the queue, if we start U in as the only element of Q0, the index of the queue that contains a particular node will be precisely the distance of that node from U. So if I want to know how far is 7 from 1, then 7 is in Q3. That means it is distance 3. And that can be verified by looking at that 1, 2, 4, 7. That's 1, 2, 3, distance 3. Now, of course, if you look at the path, then, well, in this case, this would coincide. But if I look at 7, but if I look at 3, for instance, the depth first is going to give me a path 1, 2, 4, 7, 3, which is of length 1, 2, 3, 4. But from breadth first, I know that 3 is in Q1, therefore it is of distance 1 from 1. Similarly, 5, well, the path in depth first is 1, 2, 4, 6, 5 of length 1, 2, 3, 4. 1, 2, 3, 4, whereas the Q's in the breadth first indicate that 5 is in Q2, which means 5 is of distance 2 from 1, which of course you can easily see, 1, 3, 5. This is of distance 2, and similarly 3 is of distance 1. But the paths that we get from the depth first construction would give us a path of length 1, 2, 3, 4 from 1 to 3, and of length 4 from 1 to 5, even though that is obviously not the actual distance. So the Q's of breadth first will precisely give us the distance of any of the nodes in a particular Q, Qi, from the starting node, namely distance I. And so that answers the third question. What is the distance from U to V? So we have here a situation where a path and the distance are not really quite where we would like them to be, because obviously if you ask, give me a route from here to San Antonio, and the answer is, yeah, well, you first go to Dallas and then you go from Dallas to San Antonio, you probably won't be very happy with that answer. It's not going to be what you really want. And so in a similar vein, that second question, find a path from U to V, well, we answer it, but it is probably not really what you had in mind. You may have asked, give me a route from Houston to San Antonio, and it gives you a path, but it is not really what you want, because actually what you want is a shortest path. Okay? And so the question is, how do we get a shortest path? That's, of course, a bit of a problem, because as we've seen already, the process that gives us distance, breadth first search, doesn't really give us a path. The process that gives us path doesn't give us any distance information. According to the depth first visit of that graph we're working with, the distance from 1 to 5 is 4. 1 to 3 is 4. Well, that's obviously false. We have paths of length 4 from 1 to 5 and 1 to 3, but that isn't the distance. The distance is the minimal length of any path, and obviously looking at the graph we have, the minimal length of any path from 1 to 3 is 1, and from 1 to 5 is 2. And so the fact that our depth first algorithm tells us, well, there are two paths of length 4, one from 1 to 5, the other one from 1 to 3, isn't particularly interesting. What we really want is a shortest path, and that, of course, is the question 4. Find a shortest path from U to V. And that turns out to be somewhat more complicated. Because basically, in this case, we have to construct a new graph. So given G, V, and E, construct G0, a new graph, which is V0 and E0. And V0 is the set of all nodes in V that can be reached from U. So we have U and graph, well, it should be actually here. So starting node is always given. And so we have graph VE and U, and we construct a new graph V0, E0, where V0 is the set of all nodes in V that can be reached from U, and E0 is the set of all nodes, I'm sorry, the set of all H's, from a node in Qi to a node in Qi plus 1. Set of all H's in E. So both V0 is a subset of V and E0 is a subset of E. Now, restricting your attention to all the nodes that you can reach from the node U is sort of straightforward. The interesting thing is the E0, because basically we're now saying we're only looking at edges that go from one node in Qi to another node in Qi plus 1 for I greater or equal to 0. So obviously we start with U and then we go to the Q1 and we put the edges in as they arise. And then for each of the nodes in Q1, we connect them up to the nodes in Q2 as the case may be, and so on and so forth. So if we look at this, we had node 1, which of course was connected to 2 and 3, and that was, if you look at the Q's, there was Q0, this is our U, and then Q1 is 2 and 3. So we connect them up to 2 and 3. And then 2 went to 4, and 3 went to 5. So in this case, we had 2 and 3 gave us 4 and 5. But the way these things are connected is that 2 went to 4 and 3 went to 5. And then 4 went to 6 and 7. And that was it. So this is now our G0. Okay, now this G0, of course, does not contain the node 8, because the node 8 couldn't be reached. And it does not contain a number of the other nodes. How many nodes, of the edges. How many edges did we have? We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We had 10 edges in the original graph G. And this new graph G0, which is derived from that graph, has only 1, 2, 3, 4, 5, 6 edges. And so each edge goes from a node in a Q with a particular index to a node in the Q with an index 1 larger. So Q0 to Q1, Q1 to Q2, Q2 to Q3, and these are exactly the nodes that are in the Qs 1 and 2 and 3 and 4 and 5 and 6 and 7, but they're now connected according to how the edges in the original graph G function. And so in each of these we have those edges, and that means that now we can very easily see one crucial property, and that is that any path in G0 from U, of course, is a shortest path in G. So as you can see, those bad paths that we really didn't care for, from 1 to 5 and 1 to 3, well, now it's clear from 1 to 5 is of length 2, and from 1 to 3 is of length 1. Before, depth first gave us a path of length 4 in each case. So that means in this particular case, we have a path 1, 2, 4, 7 of length 3. That's as long as it gets in this graph starting from 1, or from 1 to 4 to 6. And so what is important is, because of the construction, we always go from one q to the next higher index q, qi to qi plus 1. We get one further away from the starting node u, which is 1 in this case. And so that means we are now clearly constructing a graph in which any path in that graph that we've just constructed, any graph in that graph, any path in this graph is going to be a shortest path in G. So what that really means now is, in order to be able to answer that fourth question, find a shortest path from U to V, we first have to construct this graph G0, and then we apply, and that of course requires us to use breadth first, and then we apply depth first to that graph G0, because any path in G0 is a shortest path in G. So if we now apply depth first, it won't give us any screwy paths that are way too long, because any path in this graph G0 is going to be a shortest path in the original graph G. And so now we will find a path in that graph G0, which then will satisfy question 4. We want a shortest path from U to V. So, let's pause at this point. We've managed to answer the first 4 questions. Can we reach V from U? Either one of them. Can we find a path from U to V? That requires depth first. What's the distance from U to V? That requires breadth first. And find a shortest path from U to V. That requires us first to construct this new graph G0, and then apply depth first. So before we go on, let's look at the complexity considerations. We have to look at what are the various complexities of the two algorithms. We have depth first, and we have breadth first. And so in both cases, we'll look at space and time. So in both cases, we of course have the array visited, which requires in space. This is visited. And then visited. And then we have to, in depth first, we have to do the recursion. And so the question is, how big can the stack become? Well, the stack is of size n in the worst, n minus 1. So order of n for the stack. Plus some runtime variables, simple variables to just control things. So that clearly gives us a space complexity of order of n. For breadth first, basically the Q's will require at most n space, because not all nodes may be reachable. So basically the queues will contain exactly all those that are reachable. And so since there may be n that are reachable, we need space order of n plus some runtime variables, which again is order of n. So in both cases, the space complexity that we will have to deal with is order of n. Now, in the case of the time complexity, it turns out that we have to differentiate between the two representations. Now, the array visited, of course, will have to be initialized, and then it will have to be changed. We probably have to set it all to false and then put in true. So in the worst case, that would be n plus n if all of them become true. So that's for the array visited. And now we have to differentiate between adjacency lists and incidence matrix. Because if we do the adjacency lists, then remember we said that we have m edges and n vertices. So the space, the time for the adjacency lists, basically in depth first, we're going to look at every edge at most once. At most, because some edges may not figure in that. For instance, if we look at the edge from 8 to 7, well, we will never have to consult that edge. So in the worst case, it will be m edges that will have to be considered. And so in depth first, we're going to look at m, which is, of course, order of n plus m. In the case of the incidence matrix, we will have to look at the entire matrix in the worst case. Why? Well, if you look at this, if you encounter a node I that has to be inspected, then in order to go with the adjacency list, you just go through the list. So if there are only 2, then that's all you need to do, 2 operations. In the incidence matrix, even if there are only 2 entries that are true, you still have to go through the entire list, the entire row, which means that this is order of n, and that means that this is order of n squared. So this is equal to order of n squared in time, if it's incidence matrix. If it's the adjacency list, you have basically n plus m. This is sort of the standard kind of thing. For breadth first, you have array visited, and now you're looking at the queues. For the adjacency lists, again, you're going to look at m edges at most. So if there are m edges, then that's no, you don't need more than that in order to do that. And so that means this is order of n plus m. And in the incidence matrix, same story as before. You will have to look at the entire row, and that means if you encounter n nodes, you will have to look at n times n entries in the matrix, which is n squared, so that gives you order of n squared. The upshot of that is that the complexities in both time and space of both depth first and breadth first are identical, even though they look very, very different in the processing. The depth first is an inherently recursive algorithm. Breadth first is clearly an iterative algorithm that manipulates queues. The time and the space complexities of both of them are identical, and they're even the same whether you have it represented as adjacency lists or as incidence matrices. It's the same. So what that means then is we have to revisit our 4 questions that we've answered so far. Can we reach V from U? Well, the time complexity obviously is whatever you want. Depth first, breadth first, it's the same thing. It's what we've just derived, a space complexity order of n in both cases, time complexity if it is adjacency list n plus m, if it is incidence matrix n squared. So that's the first question. The second question is find a path. Well, that's depth first. We've just answered that. Depth first is this, and that means we simply do depth first, and complexity, time, space complexity, order of n, time complexity, n plus m, or n squared if it is incidence matrix. So that's the question number 2. Question number 3, here. Question number 3, distance. Well, as we said, that requires breadth first, and breadth first, of course, is here. Space complexity n, time complexity, adjacency list n plus m, incidence matrix n squared, all of which we've already answered. Finally, question number 4, shortest path. That's really what we're interested in. And now what that means is we first have to construct this graph G0. How do we get this graph G0? Well, we go through the breadth first construction, and basically instead of constructing a new graph G0, we can carry this out, so we simply delete all the edges for a particular node that is reached. So this would be first 1, where we start, and then 2 and 3, and then 4 and 5, and then 6 and 7. So we delete all the edges except for the ones that satisfy that definition. That then gives us quite clearly the graph G0. We may then get our V0 by consulting the array visited. It doesn't really make that much difference if you actually use V instead of V0, as long as your edges E0 are okay. Your depth first search is not going to give you anything wrong, because it will reach only the things that can be reached. So what that means is at this point, we construct this graph G0, which really requires no more time nor space than the breadth first construction. So this is breadth first. We have that to get G0. And then we apply to that graph G0 depth first, which of course is again this. So basically we apply first breadth first, and then we do depth first, and so that is in essence twice the whole thing. But given that we're typically doing order of, we have exactly the same complexity as for either depth first or breadth first. And so finding a shortest path, even though it may look a little bit more complicated than either of depth first or breadth first, is really exactly of the same complexity, both space and time. So that means we have now put to rest the first four questions. So we finally have to go and look at the last question. Find all shortest path. This will actually turn out to be somewhat surprising, because you will discover that things can get rather nasty. How nasty? Well, here is a graph. We have starting node 0, and then the construction as it goes to numbers I and I prime. So 0 goes to 1 and 1 prime. 1 goes to 2 and 2 prime. 1 prime goes to 2 and 2 prime. Then we have 3 and 3 prime. 2 goes to 2 and 2, and 2 goes to 3 and 3 prime. 2 prime goes to 3 and 3 prime, and so on and so forth. We go to n minus 1 and n minus 1 prime, and n prime, n minus 1 goes to n and to n prime, and n minus 1 prime goes to n and n prime. And finally we have n plus 1, where both n and n prime go. Now, this is our graph G. So it has altogether 2n plus 2 nodes, and each node, except for n prime and n plus 1, has exactly 2 edges. So there are 2n, because from 0 to n plus 1, from 0 to n minus 1, these are n, and each of them has n edges. So 2n for all of these, plus those 2. So these are, no, that's not true, 4n. Okay, we have to be a little bit more careful. For 0, we have 2. For n and m prime, we have 2. And then from 1 to n plus 1, n minus 1, there are 2. 2 n minus 1, there are 2. Okay, because everybody, I need 2 because everything occurs primed and unprimed. So this is for 0, this is for n and n prime. And this is for everybody else, because everybody else occurs in 2 different versions, primed and unprimed. I need that 2. There is 1 through n minus 1. This is n minus 1. And then each of these has 2 edges. So this is 4 plus 2 plus 4n minus 4. So this is exactly 4n edges. Okay. And now the question is, how many paths are there from 0 to n plus 1? Well, if you ignore the last two, the n prime and n plus 1, then there are exactly n minus 1 from 0 to n minus 1. Along this path, you always can choose whether you go left or whether you're going to go right. So this is left, this is right, this is left, this is right, left, right, and so on. So for each of these nodes from 0 to n minus 1 or n minus 1 prime, there are two possibilities that you can take. You can go left or you can go right, which means because there are n of them, every possible choice of these 2 to the power of n ways is going to give you a new path. I can go left or I can go right, I can go right, I can go left, right, left, 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 right. So basically, left and right you can encode as binary numbers 0 and 1, and so that means you have basically n places where you can put either a 0 or a 1, and each binary string of length n is going to give you a different path. So they're all together 2 to the n paths, all of which are shortest, and all of which will get you from 0 to n plus 1. And so that question number 5, is radically different from everybody else. All of the first 4 questions are essentially of a very benign time and space complexity. Question 5 is still of a benign space complexity. It is not any different from finding a shortest path from u to v, but the time complexity can be awful, as this clearly indicates, because there could be 2 to the n paths, so that means you'd have time complexity 2 to the n to find all shortest paths, even though there are only order of n nodes. The space complexity is not going to be any different, because basically you do, well, first of all, if you look at, I forgot to say that, G0, of course, is exactly G, because this is already stratified. The numbering is such that it is clear. This is of distance 1 from 0, distance 2 from 0, distance 3 from 0, distance n minus 1 from 0, distance n from 0. So that is clear. And so the construction of the G0 is same as before. Nothing has changed. And so the only difference is the application of the depth first. So the algorithm then, in depth first, if you look for v, you stop once you see it. Now, we said already that if it's unsuccessful, you just keep on recursing until you are reaching the termination condition, namely that you have nothing else to recurse on. If you don't stop after you've found the first v, which is of course the path from u to v, if you then continue, you output the path, and then you continue pretending that you haven't seen v yet, then you will encounter v possibly again. And that will give you the next path, and then you continue again. And in that way, you are going to go through all of the paths, and as this indicates, this can have 2 to the n paths, so this requires order of 2 to the n time. The space complexity is still the same as this. It's order of n, because your depth first, because your stack will never exceed n a minus 1 in length, so that is not going to be a problem. So the space complexity is still going to be order of n, but yet the time complexity, of course, is now crucially dependent on the number of paths, and in this case, this can be easily exponential. Any questions? So that brings me to the end of what I want to talk about graph algorithms. There is going to be a small modification. I am going to do things a little different in order. I am going to do on Wednesday, sections 6.4 and 6.6, which was originally scheduled for April 20th. So I'm interchanging basically what I had originally given you for April 8th and April 20th, meaning that I'm going to do the sections 6.4 and 6.6 on the 8th, and what is scheduled for the 13th is still there, and what was originally scheduled for the 20th is 20th of April is going to be on the 8th, and what was scheduled for the 8th is going to be on the 20th. Other than that, there's not going to be any change. All right? Anything? Questions?
So the test is still on the 15th.
Complaints? All right, then I will see you. I will talk to you on Wednesday.
I've got a question.
Bye-bye.